Hi, my name is Zhe Huang. I'm delighted to present our research titled Fix a Step, Semi-supervised Learning for Uncurated Unlabeled Data. This is a joint work with my colleague, Mary Joy, Dr. Ben Wesser, and my advisor, Professor Mike Hughes. In this study, we address the challenge of using real-world unlabeled data for semi-supervised learning. Throughout this presentation, I will outline the motivation behind our research, the key components of our method, and the results we obtained through extensive experiments. Semi-supervised learning is an important subfield of machine learning. It emerged in late 1990s as researchers sought to address the scarcity of labeled data. Many approaches have been developed, such as self-training, co-training, graph-based model, generative model, etc. In this study, we focused on the methods that train a deep neural network using labeled data and unlabeled data simultaneously. With the loss function constructed by two terms, a loss that encourages accurate prediction on the label set, and a loss that encourages smooth or consistent prediction on the unlabeled set. Many recent SSL methods fall into this category. While promising, current SSL methods have been mostly prototyped and benchmarked on artificially clean unlabeled set. For example, using a subset of CR10 as labeled set and the rest as unlabeled set by artificially forgetting known labels. This is also called the closed set SSL. This is very different from the real application, where the unlabeled data is often collected for convenience and lacks strict validation, resulting in what we call uncurated unlabeled set. This uncurated unlabeled set may contain out of the distribution classes or estimate different class frequency or image feature distributions. Previous research, such as Oliver et al., has shown that current SSL methods struggle with uncurated unlabeled data. Safe SSL have been proposed. Recent complex remedies often involve filtering or downweighting OOD samples, based on the assumption that OOD samples can only negatively impact SSL. But is this assumption always valid? In this study, we argue for a new paradigm where we view all unlabeled data, including OOD samples, as potentially helpful. Following this paradigm, we introduced Fix a Step, a new training procedure that improves any off-the-shelf deep SSL methods on uncurated unlabeled data. Finally, we created a new SSL benchmark called heart-to-heart for benchmarking SSL under uncurated unlabeled data. In order to understand our methods and experiments, I would walk you through the CR10 6-animal task originally introduced by Oliver et al. The label set contains the 6 animal classes. We are going to construct multiple unlabeled sets of the same size but different level of mismatch or contamination. For example, at 25% contamination, the unlabeled set contains 4 classes: airplane, dog, frog, and horse, with airplane being an OOD class More details can be found in the paper. We highlight several findings. First, our experiment confirmed the observation from Oliver et al. For various deep SSL methods, as the level of contamination increased, the accuracy of this method decreased. Second, we found that even under ideal OOD filtering conditions, where all OOD samples are removed, but every in-distribution samples remains, off-the-shelf SSL method still underperform. This suggested that methods focused only on OOD filtering are inherently limited. On the other hand, our proposed method, when applied to repair off-the-shelf deep SSL methods, significantly improved their performance, leading to robust SSL. Compared to safe SSL methods, fixed stat plus fixed map achieve better performance across all tested levels of contamination. Fixed stat is also considerably simpler, with no additional loss term, no additional neural networks, and no complex bi-level optimization. We now introduce the two key components in fixed stat: an augmentation phase that makes use of all unlabeled samples, and a step direction modification phase that prevents possible harm from the unlabeled loss. The augmentation phase employs mix-match style transformation to create new image label pair for label set, using labeled and unlabeled images while mixed up. Although mismatch style transformation has been successful in closed-set SSL, its effectiveness in open set was not verified. Our finding confirmed that such transformation remain valuable. Below, we show a motivating example. We see that contamination level increase, the accuracy of mixed match decrease. However, including all the unlabeled data is always better than perfect OOD filtering. But augmentation alone is insufficient, as mixed match perform worse than the dashed line, which is the label-only supervised training, indicating the need for additional improvements. Our fixed stat, shown in red, successfully improved the simpler and older methods from 2013 to outperform the more advanced mixed match from 2019. In addition, our method also modified gradient descent updates. Recall that the total loss comprised a label loss and unlabeled loss. Another way the unlabeled sample affects training is by the unlabeled loss. In gradient descent, we get a gradient term for both losses. Without modification, we will step in the direction that is the sum of the two gradient vectors. However, reasoning that our ultimate goal is to effectively classify the label set classes, we propose to measure the compatibility of the two losses at current step by examining the angle of their gradients. If the gradient point in opposite directions, indicating the unlabeled loss gradient will counteract improvement in label loss, we ignore the unlabeled loss gradient. We prove that this update rule always gives a decent direction of the label loss. We also consider a clinically relevant SSL task using echocardiograms. Echocardiograms are the gold standard for diagnosing many heart diseases. Each scan, called a study, contains dozens of images showing a different 2D view of the heart. the task we use is view classification, where the classifier is trained to distinguish 4 view types: PLABS, PSTAT, A4C, and A2C. We train the SSL classifiers using TMAT2, an open access dataset our team released previously. We train on around 1,600 labeled images, as well as 353,000 unlabeled images. We emphasize that the unlabeled set is truly uncurated from real routine scans of more than 5,000 patients.
We now introduce our new benchmark called Heart-to-Heart, designed to stress test semi-supervised learning on a real clinical scenario. After training on our TMAT dataset, view classifiers are assessed on test images from new images from our Boston-based TMAT dataset, as well as patients from 2 European hospitals. We took 2 open source datasets, one called Unity that contains echoes from 17 hospitals in the UK, and another that contains echoes from 1 hospital in France. By testing on these 2 external datasets, we're able to determine how well the model generalized to images that with perhaps different population demographics or images being taken on different medical devices. Across the external 2 datasets, we were able to test the balanced accuracy of the model on all available A4C, A2C, and PLAX view images. In this figure, we compare the performance of classifiers trained with and without FixaStep. On the left panel are the results for the TMAT test set. From these results, we can conclude that semi-supervised methods with FixaStep significantly outperform the classifier trained only on labeled data. On the right are the results for the Unity dataset. From these results, we see that the gains and balanced accuracy from FixaStep are not isolated to the TMAT test set, but rather transfer well to the Unity dataset, a dataset that comes from a hospital that does not inform model training at all. To see how gains also transfer to the French dataset, please read our paper. We hope our new open access heart-to-heart benchmark encourages the semi-supervised community to move beyond the same old datasets and assess generalizability and transferability on a real medical problem.
In this work, we've tackled the problem of realistic SSL in which the unlabeled dataset may be collected for expediency and thus uncurated. We claim 3 contributions. We've argued for a new paradigm for SSL in which all unlabeled images, even those from OOD classes, should be viewed as potentially helpful. We've introduced a new training procedure called FixaStep that can help many common deep SSL methods perform better on uncurated data. Finally, we have a new open access benchmark called Heart-to-Heart with realistic uncurated unlabeled data from a real medical problem and the ability to test cross-hospital generalization on data from several countries. Future directions could explore many questions. Can FixaStep improve SSL on other data modalities beyond images? Can we justify mix-up augmentation more rigorously beyond its empirical success? And can we address feature distribution mismatch in the uncurated data? Thank you for your attention. Please try our open source code at the GitHub link. You can also at that link find instructions for the Heart-to-Heart dataset.